I'm going to demonstrate a virtual catalytic reactor laboratory that we've created as a possible substitution for a physical laboratory, and I've given the location of the simulation, and the idea is that students can take data and then analyze the data to determine kinetic parameters. And so the system represents something very similar to a catalytic reactor in the lab. It shows two feed gases, and the valves are closed here, so you can see a blue and a red section. That represents the gas, because this is before the reactor system is started up, at which time these valves are open and the gas flows through mass flow controllers, then flows through a packed bed reactor, and then goes through a sampling valve, such that when this valve is switched, this volume is injected into a GC, which is then analyzed. And the idea is that data can be taken at different pressures by changing the pressure with the controller here, and can be taken at different flow rates of each gas, and then that data can be used to apply nonlinear regression and back out kinetic parameters. There's 3 kinetic parameters for this Langmuir-Hinshelwood expression, so it takes a significant amount of data to get kinetic parameters with reasonable accuracy. So once someone logs in, the data is kept in a data log that they can download. The user can come back at a later time. Their data will be saved. Each user has different values of kinetic parameters. And the simulation contains quite a bit of documentation to explain the details, and also explains nonlinear regression. I'll now go to the website and let's look directly at the simulation. So here's the simulation, and when I select Startup Reactor, you'll see that the valves open. We start up the gas chromatograph and we inject the calibration, 3 components, 2 reactants and 1 product. We open the valves so gas flow goes through the preheater and the reactor, and then through the sampling loop, and is exhausted. And then the system is increasing the temperature in the sand bath to a preset temperature, and now it's ready to make measurements. So if I select this sampling valve, then the volume of gas trapped in that sampling loop is now injected in the GC, and the analysis is displayed on the screen. And then if I click the GC, it gives the mole fraction of the 2 reactants and the products for this particular condition. I can make additional measurements now by changing the flow rate. This gives the range, the flow rate that can be used. So I can change this to a lower flow rate, keep the flow rate of the other reactant the same. I can also change the pressure. So let's increase the pressure, and now I can switch the valve back so it's again collecting sample from the reactor, and once it's done that, it's ready. I can click and you can see it's making a measurement. The screen now displays the amplitude of a GC output, and then this shows how much of A is left, how much of B, and then how much of product C formed. So the idea is the simulation can be used to gather data for range conditions by changing the 2 flow rates, changing the pressure. The data then is logged, these 2 measurements, so I can download this into Excel. Download as a CSV file. There's quite a bit of documentation that explains essentially the learning objectives, goes through details of the simulation, shows some assumptions we're making, explains a bit of what I explained here of how to get started, and talks about how to acquire data. This is a video of an actual laboratory reactor system that's doing the same thing. And here we have a number of screencasts that one explain the Langmuir-Hinshelwood mechanism, and then the others explain nonlinear regression and show how to determine kinetic parameters of nonlinear regression using, for example, in this case, Excel. And for students, they can submit their answer to their instructor. Here are some questions that after completing the lab you should be able to answer, and this explains who did the programming and some other additional information about the simulation. So the idea is this probably takes significantly less time to collect the data than an actual laboratory reactor, but there's still significant planning as to which conditions to pick, and then significant analysis to back out the kinetic parameters.